This lecture is a description or a continuation of talking about multi-electron atoms and the quantum mechanical configuration of how the electrons are distributed around the nucleus in these atoms. And so in a previous video, I said that. So in a previous video, I was trying to indicate that you could imagine starting from a bare nucleus, right? So just protons. And then you start, or then you build up your multi-electron atom by starting to fill electrons in the lowest energy level, right? And you just filled out these quantum states. You start at n equals to 1, and then if you need to add more electrons, you then go into n equals to 2, which has both s and p subshells. And then if you still need to add electrons, you go into n equals to 3. And then if you still need to add electrons, right, you go into n equals to 4. You don't skip ahead to n equals to 15 or something like that, because that indicates that you have an excited state. Okay, so I said that, and that makes some sense, but it turns out that there are energetic exceptions. And these exceptions really are, there are exceptions and then also sometimes exceptions to the exceptions, right? Lots of rules. And predicting these exceptions to exceptions and figuring out all of the fine points and small fine rules is actually really, really hard to predict, but you can see the rules in the spectrum that comes away from these complicated atoms. So I'm just going to give an example of seeing some of these exceptions and exceptions to exceptions, right? But remember, what we're talking about is we start from the basic assumed rule that you just fill n equals to 1, then 2, then 3, and on. And I'm about to show you an exception to that rule, and then I'm going to show you actually an exception to the exception of that rule as well. So let's first look at argon. So argon's atomic symbol is Ar, and I've got it in this volume 3 of the OpenStax university textbook, university physics textbook. So here is argon. I don't know if you can see my little circle. I think I'm on the screen. It's right next to argon. It's the furthest over to the right and 3 rows down. So if you go over to the right side, you see helium at the top, then neon, then argon. Argon is one of these noble gases. And let's quickly think about how we fill in the electrons to a bare argon nucleus, right? So argon's Z number, right, proton number, let's count it. Starts at hydrogen, hydrogen's 1, helium's 2, and then lithium is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So argon is 18 protons. So let's go back to the notes. So argon is Z equals to 18. So let's build up the quantum state for the electrons in an electrically neutral argon atom. So you start with n equals to 1. There is only the option of the s suborbital, and I can put 2 electrons there. So there is 2 electrons here. And then I have to bump up to n equals to 2. So I go up to 2, and the first thing to fill is L equals to 0, and I can put 2 there. So now I have 2 more electrons, right? So far I've accounted for 4 electrons, and I have what's left over, 14 electrons to fill. So I've still got a p orbital, right? When n equals to 2, I can also have the option where L equals to 1, right? That's called the p. So let me erase that. Okay, and in the p orbital is described by the fact that m sub l can take 3 different values, but for each m sub l value, there's 2 spin values, so that's a 6, right? So far, I have now 10 electrons accounted for, so I need 8 more, but I've exhausted all of the options for n equals to 2, so I have to go up to n equals to 3. I start in the s orbital, and I can put 2 there, so there is 2 more electrons, so that's 10 plus 2 is 12. I have 6 electrons left, and the next orbital to fill is p. So p, I can put 6 electrons in a p orbital. So here's 6 more, and 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 more is 18. So there are all 18 electrons accounted for, and this right here is the configuration of the ground state of argon. Okay, but let's look at a different atom. So let me go back to the textbook. So argon's over here, third row down, far right side. And let's go over and look at, for example, calcium. Right? So in order to get to an electron configuration of a neutral calcium atom, right? I keep saying neutral because what that's going to say is, you know, calcium is 2 elements beyond argon. Argon had 18 protons, so calcium has 20. And this calcium, neutral calcium atom, we have to account for, because it's neutral, 20 electrons in the ground state of calcium, obeying the Pauli exclusion principle. So no 2 electrons in the calcium atom can have the same quantum number. So I need to have 20 different quantum number combinations, right? And so if you look, argon was at the end of the 3p. So to get neutral argon, I needed to use all 6, right? I placed all 6 3p, well, yeah, so I have 6 electrons occupying the 3p subshell. To get to calcium, I just bump up and add 2 more electrons in the 4s. And you might think, okay, so to get to the next atom, and here is one of the exceptions, in order to get from calcium to whatever Sc is, right? I actually don't even remember the name. Is it Scientinium or something? Or I'm embarrassed that I don't know, but you can look it up if you want. So calcium, if I want to add an electron, you might think, right? I just follow the pattern. I go from 3s to 3p, 4s. Why don't I just go into 4p, right? If I want to go to z equals to 21, which is what this Sc is, and it turns out that that's not what I do. It turns out that what I do is actually drop in n value. Can you see I go from 4s into 3d? So I drop in n value, but go up in L value. I go to L equals to 2. So let's write down what we think chromium should be. Chromium is Cr. I happen to know that that is chromium, right? In the 6th column, in the top row that you can see, the 3D row. So I start with argon. So I've got an argon noble gas base, and then I'm going to add 2 electrons to 4s, and then to get to chromium, I'm going to add 4 electrons to 3d. So how am I going to do that? So let's go back to the notes. So chromium is 22 plus 4 is 26. Z equals to 26. And it seems like what I need to do is, so start in 1s, right? Seems like I should expect this as my answer. So I go 1s2, 2s2, 2p6, 3s2, maybe 3p6, 3d, right? So the d orbital is L equals to 2. So that means m sub L has 5 different values, right? But m sub S is 2 different values. So that means that an L equals to 2 can hold 10 electrons. That is, there are 10 quantum numbers that are different that are d suborbital quantum numbers. So 10 electrons. So I can put 3d 10. Let's see how many electrons I've accounted for. So 2, 4, 10, 12, 18, right? So 18 plus 10 is 28. So actually I don't need all 10. I just need 8, right? I could have had 10 electrons in the d orbital, but since chromium is 26, if you add all these, right, 2, 4, 10, 11, 12, 18, that's 26, right? And it turns out that this is not the behavior, this is not what chromium behaves like in a chemistry sense. This turns out to be the wrong answer. And it's actually only wrong starting here. That's where the wrong answer starts. The right answer is to have all the same stuff here, which is, if you think about it, this is still argon. Can you see this is a repeat of argon right here? Everything's the same. So argon is sort of the base, and now we're going to add valence, right? We're going to add valence. So we have an argon base, which is everything in this square bracket. And then instead of going to 3d, actually we bump up and add 2 electrons to s first. And then we back off and start filling the 3d level, the 3d suborbital, or subshell. So I've got 4s2, and then it turns out, right, I have to add 4 electrons. So this is 6 electrons beyond the 18 of the ground state of argon, or the neutral atom argon electron count. So I add 6 more, and I get, oh shoot, no, that doesn't sound right. Let's see. Let me make sure. Maybe I've got this wrong. That Z is 26 for chromium. Let's go recount for chromium. So, oops, no. Back for chromium. Let's count. So argon's 18. Yes, can you see? Here's 10, 11, 12, 13, 14, 15, 16, 17. Am I miscounting something? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 for argon, 19, 20, 21, 22, 23, 24. Oh, chromium was 24. Excuse me. So chromium is actually 24, which means, oh yeah, so I had 18, and to get to 24, I need to add 8 more. Yeah, so okay, that makes sense. Yep, okay, so Z is 24. Okay, so there are 18 electrons accounted for in argon, and then we're going to add on 6 more to 18 is the 24. Okay, so this is the correct answer. Turns out before filling, right? So instead of going from S to P, you don't go from 4s to 4p, you actually fill 3d, which is weird. You actually have to go down in principal quantum number and up in L. So it turns out before filling for P, you must fill 3D. And actually, the strange story actually started here. Well, not really. Let me take that back. So okay. So it turns out before filling 4P, you must fill 3D. And this is an exception. But now I'm going to tell you about another exception. So the other exception is really strange, actually. It turns out that sometimes when you look at argon, when chemists and scientists look at argon atoms, the behavior of an argon atom in the ground state actually doesn't even look like this one. So this is correct. I'm making a guess. Maybe this is correct, say 40% of the time, right? That's a 40. Sorry, it's really hard to write clearly on this thing. 40% of the time. 60% of the time, the correct answer is actually stranger. The correct answer, it starts with argon 18 as the sort of noble gas base, right? And then it definitely adds 4s2. And then what's interesting, actually, it doesn't even definitely add 4s2. It actually only adds 1 electron to 4s, and then instead of 4 electrons in 3D, it puts 5 electrons. So this is like an exception to an exception. And if you compare, so if you compare against argon 18 with the ground state configuration where you actually do fill the s orbital first before moving back down an n number and up an l number, and you do it this way, right? These are slightly different. I believe that this configuration here is slightly higher in energy than this configuration above, right? So if it's slightly higher in energy, then this is actually not the ground state. This one is the ground state if it is slightly lower in energy. And that's the sense in which for cold argon atoms, right? So if you have cold argon atoms, you have you're more likely to see the lower energy version of the ground state of argon. I'm probably somewhat misusing some of the language, and I did not myself do any of the calculations to show that this version of a ground state is slightly higher in energy. But I've read this, and it's a pretty interesting exception to an exception. This is all to say, figuring out the ground state of multi-electron atoms when Z is, I don't know, some sort of bigger numbers, like going up into the 20s, and even bigger, right? So let's say, since I started at chromium, let's look at proton numbers that are bigger than 24 or equal to 24. Figuring out the ground state is something of an art. And is dependent on experimental observations, right? predictions, making predictions, are complicated, right? Exceptions to rules. So respect your local chemist, because all these things are really hard to, first of all, observe, right? These are really, really small differences in energies. I heard quoted that the difference in energy between these two ground states is less than 1 electron volt, right? That's pretty hard to see in a spectroscopic setting where you're just looking at the light. So the exceptions to the rules are difficult. There must be a catalog or list. And this must have been the subject of a lot of chemistry PhDs and some physics PhDs likely, right? This is all to say that when we are, say, thinking about proton numbers that are kind of small, so we're thinking about sort of simple atoms, we basically have the right idea. It's still complicated to calculate the energies, but we have the right idea for how to discover the ground state or predict the ground state electron configuration. But when the Z number is sort of big, and especially when the Z number is very big, the ground state configurations are more difficult to predict. Okay.